All right. I'm going to give a little bit of introduction to begin with. Thank you very much for people who have come here and those who would maybe watch us online later on. But I am excited to host today Dr. Maryam Hosseini, who is an assistant professor of city and regional planning at U of C Berkeley. So central to her research is understanding how the built environment shapes urban experiences. She integrates urban systems, computer vision, and economics to improve walkability, accessibility, and equity in cities. She develops machine learning driven open source tools that helps planners design more inclusive and resilient urban environments. And before joining Berkeley, she was a postdoctoral researcher at MIT's Department of Urban Studies and Planning and earned her PhD in urban systems from Rutgers University, uh, conducting her dissertation research at NYU's VIDA lab. So Dr. Hosseini's work tackles critical challenges at the intersection of technology, environment, and urban design, from enhancing disability access to mitigating pedestrian exposure to extreme heat and flooding. And so I think that really resonates with us here at the Enlivened Design. So really excited to hear the talk. So please go ahead.
Thank you for the introduction, Mo, and for having me. Very excited to be here. So without any further ado, just let's get it started. So with a large amount of data being continuously collected, it is very tempting to think that we now have the world at our fingertips and we can run any analysis we desire. But if we look closer, we see large gaps in the available data at the global scale. There are countries in the global south, like the
Sorry,
Republic.
Mariam, your screen is
Sorry.
paused. Okay.
Okay. Can you see my screen now? Okay. So there are countries in the global south, like the Republic of Congo, where data scarcity is all you can get. While every corner of every large US cities is captured in Google street level images, many streets of the capital of Republic of Congo, Brazzaville, are not even labeled on maps. Even within the data affluent nations such as the United States, we can observe this clear inequity in what data we have and whose interest it represents. Data availability drives where decisions are focused. For instance, while a third of the US population is non-drivers, federal transportation funds have historically been skewed towards automobile and overlooked active transportation. This pattern of systematic disinvestment is evident in the pedestrian realm, specifically in sidewalk. To put a pace on the numbers, here are some lived examples of like a lived experience of people in different cities sharing what they face daily. And the issue is not limited to surface problems and accessibility. There is a lack of reliable data on where sidewalks, footpaths, and crosswalks are. Many navigation apps still rely on road networks, which assume there are sidewalks on both sides of the roads. And as we all know, it's not a correct assumption. Having access to all services our cities have to offer is a human right. Is driving a choice, or as Peter Norton puts it, it's a surrender to the current circumstances? Is it possible for an adult non-driver to address their basic needs relying on the current infrastructure we have? To ensure that, we need to be able to do a comprehensive analysis of our sidewalks. But any comprehensive analysis of pedestrian infrastructure requires data on where sidewalks are, how they are connected, and what their condition is. While new advances in data collection and analysis provide almost live data about the traffic congestion or even map the locations and types of the trees that we have, the available data describing sidewalks is hardly enough to draw any informative picture. Without knowing the full extent of the problem, we can't properly address the inadequacy of pedestrian infrastructure. According to a 2021 study, among the 178 municipalities across the whole US, only 20% had any sidewalk data, only 11% had crosswalk data, and only 8% had surface material data available. Data collection using conventional methods is costly. That's maybe one of the reasons behind this lack of data. The data collection method that we have and then the quality of the final products are also very much impacted by who is collecting the data and for what purpose. Majority of the available data that we have right now is collected by resourceful cities, and that can lead to inequitable representation in data to inform city and policy and the resource allocation in the cities. My vision is to help overcome this data scarcity and democratize urban data. I want to enable different cities around the world to conduct comprehensive analysis of their pedestrian infrastructure. So in my research, I offer cost-effective, easy-to-implement methods to tackle data scarcity problems at two different scales. At the city scale using aerial imagery, and at human scale using street-level images. In doing so, I design scalable tools and frameworks to infer the location of sidewalks and crosswalks, map their connection, and describe their condition, such as surface materials. One of the tools I developed during my PhD research extract data about the location and connectivity of pedestrian infrastructure. There are five main methods of generating pedestrian network in previous studies. The most promising is using computer vision, specifically semantic segmentation, together with auto-rectified imagery. When I started my PhD research, there was no open source tool specifically designed to create sidewalk networks, so it became my mission to create one. I developed Tile2Net, which is an end-to-end open source tool to create large-scale pedestrian networks from auto-rectified imagery. Tile2Net is designed to be accessible to users with diverse set of skills, so they can run it very easily from the command line using just one line of the code. And you can also access Tile2Net GitHub using the QR code here. The attention that Tile2Net received upon the release, I think, was more a testimony to how much such a tool was needed. The tool also was released on Esri Living Atlas in December last year, and it has already been downloaded by around 12,000 users. Creating pedestrian networks spans multiple different fields, from computer vision to computational geometry and geospatial analysis. It requires a variety of tools and techniques for each part of the process. The pipeline that we have for Tile2Net has two main parts. The first part is a feature detection, panel A and B that you see here, where we detect infrastructure elements from aerial imagery using a semantic segmentation model that we trained. The second part is a network generation, panel C and D. Here, we take the predictions of the model in raster format and convert them into georeference polygons and then into a line and graph representation. The input of the Tile2Net, the main input, is the auto-rectified tiles. The raw satellite or aerial imagery inherently have some distortions. Auto-rectification removes these stuff of distortions and create accurately georeference images. The resulting image have a one-to-one map between each pixel in the image and the surface of the earth. The process that we use to detect features from aerial imagery is called semantic segmentation. I'm going to very briefly explain what semantic segmentation is here, only for the audience who are not very familiar with the concept maybe. So semantic segmentation models are a type of computer vision models for the pixel-wise classification. In other words, it will assign a class to each pixel of the image. But how does the model know which classes we are interested in? This is the process of training. We have to tell the model what those classes are, and we teach it to see what we want it to see. As an example here, I wanted to teach the model to find sidewalks, roads, crosswalks in this image, and create this model for me that it can actually find this in other images that it has never seen. So I created a set of labels for these auto-rectified images. So for each image, we have a label. And in this label, you can see that each of these different classes have a specific number assigned to it. And this number is actually what the model sees. And we have a specific color for each class, only for the visual representation. Then we will train the model using this pair of the data, the image and then the label. And then the trained model will then take any auto-rectified tile and output a reference map similar to the label you see here. But detecting sidewalks is also very challenging. One of the reasons is they're very fine and narrow, and they are most of the time they represent only less than 20% of the tile and also might be obstructed by bridges, vegetations, or shadow. To overcome these challenges, we need to choose the detection model that can preserve the fine local details while also taking the global context of each tile into account. We chose a model which is like a hierarchical multi-scale attention model, a transformer-based model for this task. And also another advantage of this model is that it can make differences on tiles at different zoom levels, making it very versatile and a very good choice for the tile format that we are dealing with. Semantic segmentation models, as we talked about, they need a pair of image and a densely annotated labels to be trained. So as a data for our model, we use auto-rectified images provided by Massachusetts, Washington, D.C., and New York City to train. And we created the annotation label using the planimetric polygon data, which is also publicly available. So the whole training data set was generated from the publicly available data sets. Using the existing GIS data sets that we had allowed us to automatically create large scale annotations using tile2net rather than having to manually annotate all the images ourselves. But although having access to all this public data significantly speed up the process and decrease the cost of annotation, official GIS data can contain numerous errors. As shown in this image that you can see, there were many mismatches between the annotation, between those GIS data and the auto-rectified tiles. And we need good, reliable data to train a good model. So I had to manually modify all of these. And we also used the help of a group of MIT students at that time, planning students who helped us modify a part of these data sets to train a reliable model. After the detection model is trained and we have a reliable training model, like trained model, we will use it to make inferences on all the tiles belonging to our region. So for that, we need to convert the prediction of the model in raster format to a georeference polygon. This process maps the top left corner of each pixel from the raster coordinate system, which is an image, to our desired map coordinate system using an affine transformation, which preserves the shape and distances. Additionally, in a raster to polygon conversion, the adjacent pixels with identical values are typically dissolved into larger polygons in a process called connected component mapping. Finally, to have the line representation, we need to create the center line of our polygons, and we use the dense Voronoi diagram to create the center line, which is a method widely used to create center lines of elongated polygons. And the steps are shown in this figure. So to recap, Tile2Net, it can handle the tile computation. It downloads the tiles for supported region, creates the georeference polygons of sidewalks, footpaths, and crossings, generate pedestrian network, and creates the semantic segmentation labels for each tile. Our detection model also showed a very strong performance in detecting obstructed sidewalks and crosswalks. One of the reasons behind that was the model was trained on the planimetric GIS data where pedestrian infrastructure elements were present regardless of the obstruction. So the model learned to detect them in many cases despite this obstruction, which resulted in a better connected network. Here you can see our pipeline in action. On the left, we start with the fully auto-rectified aerial tiles stitched together showing Boston Common. In the middle, our segmentation model detects polygon of sidewalks and footpaths shown in orange and blue, and crosswalks are in red. And on the right, we convert those polygons into fitted center line, preserving the topology and connectivity of that. And here is a city scale map of sidewalk networks constructed for Boston, Manhattan, and DC. One of the applications of having these type of networks is using it for different types of analysis. In a recent collaboration that we had with MIT City Forum Lab and Technical University of Milan, we developed pedestrian network-based heat exposure index. Here we combine the heat hazard, which is the mean radiant temperature, and the exposure, which was the pedestrian volume, to provide a single measure to identify hotspots. Hotspots being where a large number of pedestrians might experience high heat stress. So, which are the corridors in the city that we have both like a large number of people and also high heat. Since the release of the Tile2Net, we also received several requests from European countries to fine-tune Tile2Net for their cities. An interesting area for future research can be extending Tile2Net to cities worldwide to explore also the challenges of applying a model that is trained on US cities to another country. Here we applied it to some auto-rectified imagery from Tallinn in Estonia, and I think the result was pretty promising without any fine-tuning or modification of the model. So it kind of like signals to us that we have the capability to go for better and more accurate models in other countries. So now that we have seen the Tile2Net and how it can transform our understanding of pedestrian infrastructure at the city level, let's also explore how city surfaces, another tool that I developed, can take our insights deeper down to the very material we walk on. City Surfaces proposes a framework for automatic extraction of surface materials from street-level images. This work was done during a course of 2 years, but in the interest of time, I'm going to skip many of the technical details of the model here, which are all covered in the paper, but I can provide more information if anyone has questions. Surface materials is one of the defining features of sidewalks. It has been an integral part of many popular accessibility and walkability audit tools. Surface material can impact the safety and accessibility. Like certain materials are associated with an increased risk of falling. They can also impact the environmental condition of the cities because different materials have different heat absorption capacities, and that can lead to urban heat island effect. And also impervious surfaces can increase the risk of flooding and are important for stormwater management. Despite all that, as I mentioned, out of 178 municipalities, only 8% of them had sidewalk material data available. Unlike Tile2Net, which worked with aerial imagery in city surfaces, we work with the street-level images. Our goal was to detect 8 different classes of surface materials from street-level imagery using semantic segmentation again. One of the main challenges of this work is the lack of annotated images for sidewalk materials. Creating annotated images for semantic segmentation is very costly. On top of that, classifying sidewalk material is a challenging task due to high between class similarities and within class variation, as you can see some examples here of different classes. To address these challenges, we use active learning framework in machine learning with experts in the loop. Active learning aims at achieving high accuracy while minimizing the amount of labeled data using the feedback that it receives from the model in the process of training. Here is the city surfaces pipeline. It has three main parts. Part A is creating the initial training data set. Part B is the first active learning phase where the model learns to classify 5 classes of materials, while a new city, which is New York here, is being added to the training data. And part C here is the second phase of active learning, where we take the model in part B and extend it with three external classes of materials, getting into 8 classes that we wanted to have. And here is the initial annotation process. In the absence of any annotated data, we needed to create our own annotations. And this was part of my PhD dissertation. So I had to do all of this by myself. And so instead of annotating from scratch, I used a pre-trained HRNet, which outputs a prediction with different classes, sidewalks and roads among them, as you can see here. But so I kept only the sidewalks and road from all of those classes, put everything else to the background. But as you can see, this is not really like a neat and nice result. So it's very noisy. I had to also manually modify it to get to something like this, which is accurate and I can rely on to train my model. We can see here how the model predictions improved at each stage using the multi-stage active learning framework that we adopted. The results of a stage 5 is reached only within 50 epoch. And this is pretty good for semantic segmentation model. And you can see that at the stage 5, the predictions of the model is even better than our ground truth, because the model reaches a certain stage, which is like a pixel perfect prediction, and the human labeled annotations can hardly reach pixel perfection. One of the other strengths of active learning framework lies in the sample selection strategies. One of our core strategy was examining how like the uncertainty map of correctly classified images. In this example, you see the lighter color in the blue part shows where this is the uncertainty map. And then the lighter color shows the areas that the model was less certain in its prediction. We see that although the prediction of the model was totally correct, the model was kind of uncertain about the parts which were under shadow. So this signaled to us that the model needs to see more instances of such cases where we have part of the image in the shadow, part not in shadow, to be able to make the correct prediction. So we added more of this to our process. Also, to demonstrate how the trained model can be used to detect sidewalks in images from other sources, we compared it with the same network architecture trained on Cityscape, a standard benchmark data set. This example shows that aside from using the model to classify sidewalk materials, it can also be used to detect sidewalks from general images and to create accurate annotation labels for any sidewalk-specific studies. Also, during the active learning cycle, we detected patterns of misclassification as shown here. For example, on the top left image, you can see that the model classified the plant pit as bricks. And also you can see like on the second row on the left that the model incorrectly was classifying broken concrete as a small stones. By understanding this type of by finding and understanding these type of patterns, we added more instances of the same problem to the training data set. And then on the final result that you see in here, the model could correctly classify the similar instances without making that misclassification. The final model classifies 8 different materials with mean intersection over union of 88%. And finally, you can see the results of applying the model to our test set, which it has never seen. And you can see how even patches of different materials here were detected, or like these fine edges and fine branches and all were all captured. And here is the city scale map of surface material for each sidewalk segments of 3 different cities, Chicago, Washington, D.C., and in Brooklyn in New York City. We are almost like reaching the final stage of my talk, and this is an ongoing work that I am working on. And for the past 3 years, I have been collaborating with a multinational interdisciplinary research team, part of like a joint effort by Rutgers, where we work closely with the local government of Zambia and Congo to help them improve their targeting strategies by incorporating new and fine-level interpretable spatial features into poverty estimation. So here we decided to fine-tune tile-to-net on high-resolution satellite imagery that we had to purchase because this data is not publicly available. And we decided to detect paved roads, unpaved roads, building footprints, huts, and bodies of water, among some other classes, to create the first comprehensive map of Lusaka, Zambia, and Brazzaville, Congo, and also some of the other more rural areas in the countries. So here you can see that we started from this aerial imagery that we got from Planetoscope. But one of the biggest challenges in mapping rural and peri-urban areas in sub-Saharan Africa isn't the AI model. It's actually the images themselves. The dry season, haze, and soil reflectance and atmospheric scattering wash out the details. You see like the narrow dead roads or huts or shallow water bodies, they're almost disappearing in the images. And these are what we actually initially selected, like these images for a training set. So the haze is actually pretty low. But I use some type of standard image processing techniques, no AI here, to enhance the representation of this image and the visual features so we can use it for our training. And I use specifically the clay method here. And this is some like results, like preliminary result that you can see. We have an original image, we have our enhanced, the ground truth, and the prediction of the model. And these are some more of the image and predictions that you can see for different parts of these 2 countries. So to just recap and as a final remark, data collection is shaped by who collects it and for what purpose. Those choices influence what gets recorded and what is left out. The result is often an incomplete picture where we may not even know what's missing or how the picture is distorted. As planners and urban scientists and people who are working in these fields, we can't just use off the shelf what is available and go with the flow of the data. We have a responsibility to think critically about what is needed and also to be prepared to commit to produce the data that can reveal the aspects of the environment that would otherwise remain unseen for everyone. So together with other researchers working in the same area, we are trying our best to help draw a more realistic picture of the conditions of the pedestrian environment. And yeah, with that, I conclude. And thank you for having me. And I'm happy to answer any question that you may have.
All right. Thank you so much. Any questions from the floor? Ian.
Hi, Maryam. Thanks again for the presentation. It was really interesting. It's definitely a topic that resonates a lot with our efforts around data capture and how to manage that. I feel sorry that you had to work through so many images during your PhD. I mean, that just sounds like a Herculean task to do that. And it must have been quite mind-numbing at times. I mean, I suppose I've got a few questions around that. One is, did you develop any sort of special tool to make it easier to do, or are there existing off-the-shelf tools that make that easier? And then I guess my follow-up, which I'll ask now anyway, is around, these days, what's your thinking around that kind of data capture? Would you use crowdsourcing or gamification or some other technique to kind of engage people on that effort?
Thank you for both questions are very relevant. So about the first one, I always joke about it and say that I put part of my soul into this because it was like a very cumbersome process of going through like all of those images, and I used mostly Photoshop, I think, when I was working with it at first. But then I also started using like I started actually working with the vectors themselves and used QGIS and other tools available to actually like modify the vectors instead. But both of them works. The thing is, yeah, there are some tools available that, like you can use to refine the boundaries, but at the end of the day, it's the same process of you have to go through the boundaries of the objects and make them perfect. And the point is, I know that there is always this, like a uh, trait between accuracy and generalizability and also the amount of time that you want to put. But for me at that time, it was like, I want to make this publicly available, so it has to be as good as it can get. So I really was very meticulous about all the edges. And the result, like the model is actually now can detect all of those. So it kind of paid off. But it was a very long and daunting process. One thing that still is missing, and there are many of these tools available online. Many companies have, like online platform where you can go, even they call it like AI enhanced annotation tools that can help you. But I think gamification, and this has been something that I thought about a lot, and engaging the community or the experts of the field is the best way to move forward with it. So if we can have some process where even like let's say we have a model that can learn from the experts, like all the interactions that the expert have, then they are refining the model, like these type of masks, and then guide them through this process of creating annotations. That would be ideal because if we want to say that, oh, okay, there is this AI that can annotate for you, that AI is actually a semantic segmentation model. This is what they do. They do annotation for us in some way. But if we have something that is interactive and can be guided by the expert for creation of these masks, this is, I think, ideal.
Yeah, I mean, if you could get a partner like Google to help you, do put it there as a capture or something, just to get some initial,
Exactly.
I mean, that sort of thing could scale immensely, but it's not a straightforward
Yep.
thing just to get in place, I guess. Yeah. I have more questions, but I'll let other people give other people the chance to talk. So, I'll wait.
All right. Anyone who has a question? I have a question as well. Um, okay, well, I'll ask my question first then. So your work really reminds me a lot of this one previous work that I've encountered before, and it's called Happy Maps. And what they did is that, like, I actually interned for Dr. Garcia. Um, Right. So for those of you who aren't familiar in here, what they did is that they were looking at the street maps, like the street views and everything, and they got people to kind of rate the aesthetics of the streets, and then they developed a model of that to predict like how happy people are, depending on where they're walking, right? Because sometimes there's a shorter path, but it's like, not as good as like say going through a park, which becomes a longer path. I was just like wondering if you have like thought about kind of exploring kind of like that qualitative side of things as part of your street automatic detection and like the materials, because I can assume there's an effect to that as well with with well-being and stuff.
Yeah, that's a great question. And I'm also familiar with the happy maps. I love them. I think I even had them in some of the presentations that I had during my PhD, talking about how these type of technologies can be used. And yeah, for sure. As a matter of fact, right now we are running a qualitative studies with some of my master's students. One of them is a skateboarder, and his vision is how can we use skateboarding as actually like a means to describe the conditions of sidewalks. So his vision is they share a lot with wheelchair users because they feel like the same, let's say, tractions and problems of the surface. So we are running this study to understand the alignment between their, let's say, expectations or the risk factors that they see when they maneuver through the streets with the different types of obstacles, and see how well aligned they are and how can we use them as, let's say, like a good representation of the conditions of the sidewalks, and also use them as a mapping tool, right? And also, another goal that I have is to create this discourse between these two groups of users of the sidewalks that most of the time they don't have this platform to engage and to converse with each other, which is, I think, very important. Part of it is for me when I first started, and before I talked with this student of mine who is very passionate about the skateboarding, was I never knew that the skateboarding is actually a mode of transportation for them. And for me, this was like a realization, right? So they are not just having fun, they actually use it to get from home to school. And this type of discourse, if we can start it also, if they can understand what are the concerns of wheelchair users when they're maneuvering through the cities, what are the things that create a stressful environment for them, it can create this type of understanding between them, and then the word of mouth can go on and on. So we can have better cities without having to only enforce these type of things with policies and rules and regulations. So yeah, I am also trying my best to be in the qualitative side of the matter.
Amazing.
I remember speaking to a NYU professor who was visiting Autodesk University a couple of years ago, and he himself is a wheelchair user. And one of the things that he mentioned that really was like, oh wow, of course, was like designing or solving for wheelchair access also enables all sorts of other things like mobile delivery robots, right? So there's
Exactly.
so you have this, these interconnecting concerns or overlapping concerns, I suppose, where you can obviously enable all sorts of things if you kind of help solve the problem for one group of people.
It's
Yeah.
very true. Yes.
I mean, it's almost like, what they say about like if you design for um like the base level almost, then you're designing for everyone. Like so that's
Very
pretty cool.
true.
Anybody else have a question? All right, Jeremy.
I'm curious whether you've thought about and or done any work on sort of more of the topographical components of it. So, for example, including in, the idea of this connectivity, which might come into play for wayfinding and things like that. Being able to detect or distinguish, stairs from a ramp, for example, which would be important for accessibility. But again, route finding, right? Is within the context of this happy maps, for example, or skateboarding, right? Maybe there's a longer route that one would take because it avoids uphills, but then you'd be okay with a hill downward on the way home, for example. So I'm just wondering whether you've done any work or thought about sort of the more three-dimensional aspects, the topographical.
Thank you. That's a great question. And yes, I really would love to spend more time on that. I have like recently, I have been working with some LiDAR data to see how we can use them exactly for measuring the elevation and even like a final scale type of elevation where you have this unleveledness in the surface. And this can create lots of problems for people on wheelchair. And this actually came out of some of the interviews that I had with wheelchair users and also users of different types of mobility aids. And we had another study last year, which was accepted to the CHI this year, and that is study like whose accessibility, accessible to whom. And the question is, we have also this, like type of like a diversity within people using different mobility aids. So their preferences are also different. And we try to map different routes that each of these groups are taking, and they were different. So they wanted to optimize different types of, avoiding different types of obstacles, let's say if they are using like a motorized wheelchair, they have a very different set of preferences than someone who is using like a manual wheelchair. Or people using walkers have different types of problems and concerns compared to those using canes. So these are also like this a little heterogeneity within the data guided me to think about the elevation more in more depth. And yeah, I think LiDAR for now are our best bet to get such information. Also, we can still visually detect the stairs from some of the images if we have high enough of a resolution and ramps. But still, we cannot compute the slope correctly. So we need LiDAR for that, definitely.
All right. Anybody else?
Well, I'll ask one more if
All
so.
right.
Um, you know, I'm curious about your experience of sort of taking a model that's been trained for one state and having it apply to other states or then other countries. Like, what is your experience with the kind of what categorizations in general would allow you to say, okay, well, this model that works reasonably well in the US is going to work for these other countries? Is it level of development, infrastructure maintenance, latitude in terms of the kind of vegetation and construction materials? Anyway, I'm just curious. I don't want to put words in your mouth, but what, how does that work?
Actually, yeah. Thanks for the question. Yes. This is something that I call it like the context of the city or like urban fabric of the city. So the similarity between the the demarcation, let's say, of the crosswalks even. Because we have within the US even, we have lots of different types of how we demarcate the crosswalks. There are zebra lines, there are yellow lines, there are bricked surfaces, there are different things that we see. So it really comes down and boils down to what are the different types of like variations that our model has seen. And the closer they are to what it has seen, the better the result will be. So as one of the, I think, examples that I showed was the one from Estonia that we tried to also apply tile to net to tiles of Estonia and to see how a vanilla model, which is not fine-tuned and not ever seen like any images from Estonia can work on their images. The results are not perfect for sure, but I think it is promising. So it shows that with a little bit of fine-tuning, it should work for at least like Tallinn nicely. So because this version of the model that is right now publicly available is trained on highly dense urban areas, mostly on the eastern part of the United States. I think it works pretty well for most of the um, high density urban areas, but like with some grains of salt. Um, that also depends on many different conditions, like the vegetation, and also, as I said, like the urban fabric, like the look of the city, the feel of the city, or like the identity of the city in some ways. But it works very well for most roads because roads are very similar in most parts of the world, unless we're dealing with, let's say, unpaved roads, which are different. And this is the case in Africa that right now I am dealing with, because the unpaved roads are very difficult in some parts to even detect for human eyes. We cannot even say, is this a road or no? Or it's just like some parts between the building that are just left there. So these type of, even like the definition of what we call a road or what we call a sidewalk can also play a role. But I think there's a big chance, like a big opportunity here to take these models and apply it to other countries with a very few. Um, I think it will need, let's say, a couple of hundreds of tiles to get fine-tuned if we have close enough of the urban fabric.
Great, thank you.
Thank you.
All right. I will ask one more questions just to end things. And maybe this is like, maybe like a bigger question. You don't have to have like a full-on answer, but like maybe drawing from your experience, what would be your something that you would encourage us, like researchers or designers, like maybe some of us here at Autodesk, to do differently to help advance equity in data and in design technologies?
Oh, that's a very good question and a tough one. So I guess I think looking systematically at cities is a big step towards better understanding of it. For years, our vision and the way we approach solving city scale problems was to look at each system in isolation. So transportation system was working on its own problems, economic system was trying to solve its own problems, and these systems were kind of like detached from each other when they were solving a problem, optimizing for what they wanted. But what I think makes cities very exciting is this interconnectedness between all of these components of the urban systems and how some changes in one part impacts the other. So if we can actually try to capture this interconnectedness more in the way that we approach research and solving problems, or create tools that they can speak to each other easily, so you can have the outcome and then outputs of one tool being very easily transferred into the other, where you don't have to deal with formats of different files. And now I cannot even go to that, and then I have to save this in this, and then use another thing to convert it to another format that this other tool can use. Like very, let's say, like a very practically here, this can facilitate this type of analysis. But also another area of research that I didn't talk about in this talk that I'm actively working on is creating visual, like interactive visual analytics system for urban planners. And this is something that I think is very important in a way that we deal with visualization of the data and different formatting and interoperability of the products that we have. So this is one thing. And another one is I think looking also at a larger scale, but also like having this human scale in mind. So there are things that when we aggregate everything, we are losing them, like the people on wheelchair, or like the population that needs certain type of treatments in the built environment that for years, because we didn't have a good representation of them, they were not part of, like the decisions that we make. Even the signal timing of the traffic for pedestrians is based on the able-bodied speed. And this this is problematic. This has caused lots of problems and lots of accidents for elderly, for those using wheelchairs, for those, like with vision impairments all year long, but we don't even hear them because that's also, again, gets aggregated within the data that we have because the number is smaller. And unfortunately, the number is not smaller because we have a smaller population only. Part of it is they cannot get out independently. So we don't see them that much, not only because they're like a very like a small population, it's like the infrastructure that we have do not support them getting out easily and independently. So that's also another factor. And taking them into consideration and trying to also hear these voices that may otherwise not be heard, I think is a big step for us to move forward and make it possible for people with different levels of mobility and like ability to enjoy the same services that we enjoy every day.
Thank you so much. Very inspiring. I am a data visualization person, so it's like I'm very interested in hearing more
We
about
should
the other
talk
projects.
definitely.
But maybe that is something that we can continue. I don't know,
Oh,
like
definitely.
working. I mean, this is research connections, right? Kian.
Definitely. Very
um,
excited about that.
Very cool. Any last words, maybe Kian or?
No, just to thank you once again for, coming to speak to us and taking the time. It was so fantastic to meet you anyway in San Francisco when we were there together. And it's just been great to learn more about the work that you do and the work that you've done over the years. So thank you so much on behalf of everybody for coming.
Thank you for having me. It was really like a pleasure. Thanks a lot.
It was a pleasure. Thanks so much. And yeah, I guess everyone, thank you for coming as well. And that's the end of this talk. See you
Thanks.
all.
Okay.
See you. Bye.
Thanks. Bye.